to develop the main idea behind motion, the theory of what we call kinematics. So we'll start off by looking at the basics of motion by defining the basic quantities we need to describe the motion of an object. So first we look at what's called distance versus displacement, two very similar but distinguishable quantities that we should not and will not confuse in this class. So to start off, let's consider a scenario. If we look at the odometer of a car, the odometer of a car will tell you how many miles that the car has traveled, but not necessarily how far the car is from the original position. So let's say the odometer in a car reads 65 miles. It means you could have traveled 65 miles east, you could have traveled 65 miles north, or you could have traveled 0 miles by traveling a loop around Phoenix. So this is what I mean by right here. If you look at an odometer, it's a little dial on your car that tells you how many miles the car has traveled. So the odometer tells us the distance that we traveled, but not necessarily how far we are from where we originally started. So again, the idea being is if I start right here, I could travel 65 miles all the way around Phoenix and end up back where I originally am. And my odometer would tell me I traveled a distance of 65 miles, but I have ended up 0 miles away from my original position. So we need two physical quantities to distinguish between the distance we travel and how far we end up from our original position. So what we call these quantities are distance and displacement. Distance describes the total length traveled by an object regardless of direction or path of travel. Since distance does not consider direction, distance is what we call a scalar quantity, meaning that it does not depend on direction, is strictly a number. Okay? So for example, right here, the distance of this path traveled right here is 65 miles. So distance in this case does not take into account the direction that we travel in. Now displacement is defined as our change in position of an object relative to some starting position. As a result, since we consider locations and directions of our objects starting and endpoints, displacement is a vector quantity, meaning that it depends on direction. So for example, here, to distinguish between distance and displacement, my displacement in this case would be 0 miles since I end back up in the original direction, or I end up back in my original location, while my distance traveled would be around this entire loop, it would be 65 miles. Okay? Whereas on the other hand, if I traveled 65 miles east, that means my displacement would be positive 65 miles, as we take east to be a positive direction. Whereas if I traveled 65 miles north, that means in the northward direction I would have had a displacement of 65 miles away from my original starting position. Thus, displacement depends on our direction relative to our original location and is hence a vector quantity. So displacement. Displacement is the change in position of an object relative to some starting position. Since we consider locations, directions, or starting endpoints, displacement is a vector quantity. And yes, I know I just said this, but since it's so dang important, it's worth repeating. The units for displacement are meters. Since we're measuring the change of our position, that means we're looking at something in terms of a length, and thus we require the unit of meters. Displacement can be negative or positive, with the implication that a negative displacement means an object is moved to the left, say you move west of a location for horizontal motion, or you move downward for vertical motion, just like a number line. Okay? So the equation we have for displacement is our change in position, so it's our final position minus our initial position. Thus, it's not really the position of our object that matters, but rather the change in position that helps us determine which direction our object's heading. So if our displacement's negative, that tells us that we've ended up to the left of our initial position, whereas if our displacement is positive, that tells us we ended up to the right of our initial position. So let's look at an example of distance versus displacement. For the particle d at right, we're asked what is the distance traveled and what is the displacement of the particle. So for A, we're asked for distance traveled. So what that means is we're looking strictly at the length of the path traveled by d. We're not considering the direction traveled. So if we look at d, d goes from a position of 9 to a position of 3. So d has traveled 6, and we'll call it 6 meters here, even though there's not a specific position, or excuse me, specific units. So we'll call it 6 meters that d has traveled here, and then d turns around and travels from 3 to 5, indicating that our person, our particle d, has traveled an additional 3 meters. Or excuse me, from 3 to 5 would be 2 meters. So we have 6 meters traveled from 9 to 3, and then we have 2 meters from 3 to 5. So as a result, the total distance traveled is going to be 8 meters. We're simply adding distances of our paths, okay? Nothing more than that. So now if the problem asks for what is the displacement of the particle, what we do is we disregard the whole entire path that our object has taken, and we only are interested in what our initial position is and what our final position is. So to measure displacement, we determine the initial position and the final position. We see our initial position is 9 meters, and we see that our final position is 3 meters. So our change in position is going to be 3 meters minus 9 meters. Oh, excuse me. Our final position is 5 meters, so this should be a 5 meters right here. Excuse me, that's a typo. So we're going to see that our final position is 5 meters, and thus our change in position is going to be 5 meters, our final position, minus 9 meters, our initial position. And thus our displacement is negative 4 meters. So we can see that our object has ended up negative 4 meters, or excuse me, 4 meters to the left. The negative telling us that our object's head to the left, and 4 meters telling us that it's headed 4 meters from its original spot. And we can see that right here by a number line. If we look, we see we start at 9, and we end at 5, so that's a change of position of 4 meters, and we ended up to the left of our original location, so our displacement should be negative. So now we look at speed versus velocity. Just as there is a difference between distance and displacement, there's also a difference, a very subtle difference between speed and velocity. So speed is defined as the distance traveled per unit time. It's simply defined as the distance traveled divided by the time interval it takes to travel that distance. Hence why I have the Lightning McQueen meme up right here, I am speed or I am distance divided by time. Since speed considers distance and not displacement, it is a scalar quantity. It does not depend on direction. Speed is independent of the direction of your object. Velocity, on the other hand, is defined as speed with a direction. So velocity not only has a quantity, speed, but it also has a subsequent direction. So as a result, velocity is defined as displacement divided by the time required to travel that displacement. So since velocity considers direction, it is a vector quantity. The reason why velocity considers direction is because our equation for velocity is our displacement divided by our time. So since displacement depends on direction, so too does velocity, and thus velocity is a vector quantity. An interesting thing to note is that our velocity will have the same sign as our displacement. Because our change in time will always be positive, our velocity sign will depend on the sign of our displacement. So if our velocity is positive, that means we're heading to the right, and if our velocity is negative, that means our object is heading to the left. Both speed and velocity have units of meters per second. Again, meters for our distance or displacement, and per second or seconds for our change in time. So this is something that you need to make sure you have down, that speed and velocity are not the same. It's something that we tend to think of as the same in everyday life, but speed and velocity are just as different as distance and displacement because velocity is a vector quantity, whereas speed is a scalar quantity. Speed will always be positive, since our distance will always be positive, whereas velocity could be positive or negative depending, again, on our sign of our displacement. So an example to illustrate is that if we have two race cars that drive out to the right and to the left with a speed of 300 kilometers per hour, the velocity is going to be 300 kilometers per hour for the car heading to the right, whereas the velocity for the car heading to the left is negative 300 kilometers per hour. So both cars have the same speed, but they're going to have different velocities based on their directions. This may seem like a very subtle detail. It's not very important right now, but it becomes very important when we start getting into more complex topics within the perspective of physics, specifically looking at things like forces, momentum, and starting to look at things like motion analysis. These play a huge effect. So let's look at an example. For the particle d, suppose someone starts a timer at 2 seconds and stops the timer at 8 seconds when the particle reaches its stopping point. We want to determine the average speed of the particle over time interval and determine the average velocity over the time interval. So using the information from example 1, we have our distance traveled is 8 meters, whereas our displacement is negative 4 meters. We know that our change in time, delta t, is 6 seconds, as a timer starts at 2 seconds and ends at 8 seconds. So the time interval from 2 to 8 is 6 seconds. So our speed is distance divided by time, or simply 8 meters divided by 6 seconds, which gives us a speed of 1.3 meters per second. We get something that is a positive quantity. Whereas our velocity is our displacement divided by time, which is going to be negative 4 meters divided by 6 seconds. So as a result, we get negative 0.66 meters per second. So we can see that the relationship between speed and velocity, or the distinction between speed and velocity has a huge effect. Specifically, not only do we get different signs, again, velocity indicating that we're heading towards the left over our time interval. As we see right here, we end up towards the left original position, but we also get a different number than we do from when we calculate our speed. Thus, it's very important to make sure you distinguish between the two quantities. And again, as I noted, the sign of velocity will always be a sign of displacement, indicating that we headed to the left over this time interval. Our net change of position was to the left. We started at d, or at 9 meters, and we ended up at 5 meters. So lastly, we look at acceleration. And let me remove this little guy right here. So acceleration is defined as the rate of change of velocity. So acceleration is the change of velocity divided by change in time. So our change of velocity is our final velocity minus our initial velocity. Initial velocity being represented by v naught, naught being the little o letter, and vf, the final velocity. The units for acceleration are meters per second squared or meters per second squared as represented in mathematical notation. The idea being is that velocity is in units of meters per second and time is in seconds, so the seconds in the denominator multiplies to give us seconds squared. Typically, we associate velocity or acceleration with objects that are strictly speeding up, but this is not always the case. In addition, since acceleration depends on velocity and velocity is a vector quantity, acceleration is also a vector quantity. I do not have that down on the notes right here. It seems I would have forgotten that little bullet point, but that's something you should have down in your notes, is that because acceleration depends on velocity, it's also a vector quantity. So now we move on to the big point. Acceleration does not always refer to an object that's speeding up. In fact, acceleration could refer to, oh no, here it is. Ooh, I went off on a little tangent. So since acceleration is dependent on velocity, it too is a vector quantity. How something accelerates depends on the direction of acceleration. It does not mean that we're always speeding up. What we need to consider is the sign of the acceleration relative to the sign of velocity, because the sign of acceleration is not always the same as the sign of the velocity. So to help us consider this, let's consider a case of a car that's speeding up, a car that's slowing down, and a car that is changing direction, represented by this circular path right here, okay? So if a car is speeding up, okay, the direction of the acceleration is going to be the same as the direction of the velocity. The reason being is that if we think of acceleration as us pressing on a gas pedal, pressing on the gas pedal provides a burst of acceleration in the same direction of our motion. So when velocity and acceleration have the same direction, our object's going to speed up. However, acceleration does not only refer to speeding up. Because acceleration refers to any change in velocity, it can also refer to slowing down, or because velocity depends on direction, it can also, acceleration can also indicate a change in direction, since velocity depends on direction. So slowing down refers to when the direction of acceleration is opposite the direction of velocity. The idea being is that if we hit the brakes on our car, it's like we're providing a pulse of acceleration in the opposite direction of our car's travel, hence slowing us down. So when acceleration is opposite the direction of your velocity, your car will be slowing down or your object will be slowing down. And lastly, we have changing direction. So if we recall that velocity consists of both speed and direction, we can note that an object can accelerate even if its speed remains if the direction changes. So our speed can remain the same, but if our direction changes, that means that our velocity also changes, since velocity depends on direction. So in this case right here, our acceleration acts perpendicular to our direction of motion, which means that our speed will remain constant, but it's kind of like the acceleration pushes our car in the perpendicular direction, causing our car's path to curve. This is actually what we call circular motion, and it's going to be the main topic of study for Unit 8. And these are the basics of motion that we need for position, velocity, and acceleration.